Okay, so far we've seen lots of examples of gauge theories, and I've worked through a good proportion of the analysis in the one sort of heavily studied case, which is Donaldson theory. Last time we mentioned the higher dimensional gauge theories, where the analysis is still not done. So we have the beginnings of the compactness theorem, due to people like Tian, but transversality we don't have. So you can't make the moduli space of the right dimension while keeping compactness and so on. So it makes it very hard to study higher dimensional gauge theories because we don't have transversality. So you perturb the equations too much, you lose all those topological bounds, the compactness and so on. So the one case I was talking about, the holomorphic Casson invariant, that's one case where you don't need transversality because everything's algebrogeometric, and you can do algebrogeometric versions of transversality, and this was these virtual moduli cycles that are in the notes, but I didn't really have time to talk about. The difference, Seiberg-Witten theory is a bit different. So what we'll see is it looks rather unnatural. It's hard to describe the gauge theory. It doesn't look as nice as all the other gauge theories. But the analysis is much easier. The transversality is much easier. Compactness is trivial. So these are great equations analytically. So we have to go through a bit of nonsense to get to actually define these equations, unfortunately, because we need spin C structures. But if you find, firstly, I know Blaine's done a little bit of this, these Clifford algebras. If you find this a bit tough or quick, it doesn't really matter. The end result is just a PDE defined on a 4 manifold, and then we go through the same procedures as before. The point is the analysis is easier because the nonlinearities are easier. But for completeness, I'm going to describe how you get these Seiberg-Witten equations from spin C structures. As I say, in some sense, it's not so important. We just need to know that there is this PDE, this naturally occurring PDE, with the right kind of nonlinearities. So to do this, we need spin C structures. So the quickest way I could find of doing this in 4 dimensions is the following. So I'm only going to do even dimensional. So M will be 2 eventually, Clifford algebras. So let's do everything on a vector space. The point is just associated to any vector space is a natural algebra. Sorry, any inner product space is a natural algebra. So you could describe it in some kind of universal way as you just form all tensor products on this vector space, so all possible tensor products of elements of the vector space, and you divide out by one single relation. Or more explicitly, you can actually see what this algebra is. As a vector space, it's just the total exterior product of the vector space, so wedge 0 plus wedge 1 plus wedge 2. And it's got you use the metric to form a different product. It's not just the wedge product. That's my stick. But it involves the interior product as well. So this is the anti-symmetric part of the product. And here you can, using the metric, you can think of V as in the dual space, and then you just contract it. Okay. Anyway, so this forms an algebra. This satisfies that relation, and it turns out to be this universal algebra here. Okay, so it doesn't really matter. There's a canonical way of forming an algebra. And it acts on itself, because it's an algebra, by multiplication. So it's a module over itself, but it's a very reducible module. But there's a way of producing an irreducible module. But this is non-canonical. So we've done that canonically. So we can do that in families. We could start with a vector bundle, and we get a bundle of algebras. This bit's non-canonical, and that's sort of the key point. And again, it doesn't sort of matter what I do here. The point is just that something exists. So let me show you that. So what you do is you consider V as a complex vector space. So pick an almost complex structure on it. So it's now a complex vector space of half the complex dimension. And now form the exterior product, but over C. So this will be much smaller, because if V there is 4-dimensional, this is 2 complex dimensions. So you can only take wedge 0, 1, and 2. You can't take 3 and 4 anymore. So this is a quotient of that algebra over there. It's much, much smaller. And with the same action as before, but extended by complex linearity, we find that this is a module over that algebra. So the exterior power over the reals acts on the exterior power of the complexes. And you see that action does indeed satisfy Clifford relations, so that's good. And what you find, this is the key point. You don't need to know any of that. What you find is just that this is an irreducible representation, and it exhibits the Clifford algebra as, in fact, the entire endomorphism algebra of this vector space. Okay, so the point is you could have proved this completely differently. All you need to know is that associated to any vector space, there's an algebra, and it's actually a matrix algebra. It's the space of all endomorphisms of a vector space. So you could also have proved that differently by showing it for small n and then showing it inductively using this relation here. Okay, so we can do this in families. So associated to any vector bundle, we get a bundle of algebras which are matrix algebras. They're endomorphism algebras. And we could ask, what are they the endomorphisms of? Well, locally, they're the endomorphisms of this. But this isn't canonically defined because we had to pick a complex structure to do this. So there's going to be obstructions to finding a W such that this Clifford algebra is the endomorphisms of W. So let me say it again. Suppose V is now is a vector bundle. Suppose it has a complex structure on it. Then I can form this complex exterior algebra, and we will find that its endomorphisms are isomorphic to the Clifford algebra of my original bundle. If my bundle doesn't have a complex structure, it may be that there is no vector bundle globally whose endomorphisms are given by this Clifford algebra. So in some sense, in other words, we have this situation where, given V, that gives me some endomorphism bundle, NW. NW exists, but W may not exist. So it only exists locally, but it only exists up to the action of scalars. So the only, in other words, automorphisms of V induce automorphisms of W up to the action of scalars. This is an irreducible Clifford module. So the things which commute with the Clifford action are the scalars. So the problem is that if you do an endomorphism of this, e.g. a transition function, it doesn't uniquely give you an endomorphism of this. It just gives you one up to the action of scalars. So W is defined locally up to tensoring with a line bundle. So W defined locally up to W maps to W tensor with a line bundle. And if you tensor by a line bundle, it doesn't affect the endomorphism bundle. So this is defined globally. But if we pick it, if this is this has a complex structure on it, then this is defined globally. So in other words, the endomorphism bundle of W or the projective bundle of W are both well defined. They're unaffected by tensoring by a line bundle. But we want to know if this bundle can be lifted to a global vector bundle. And that's because there's choices locally. There's choices of the lift because you can tensor by a line bundle. So there's different choices. Therefore, there's different obstructions to patching all those choices together. So a spin C structure is a choice of a lifting. So a spin C structure is a complex vector bundle such that the Clifford algebra is its endomorphisms. That's a spin C structure on a vector bundle. Spin C structure on a manifold is the same thing for the tangent bundle. So in particular, if the manifold's almost complex, the tangent bundle becomes a complex bundle. And therefore, we can form its exterior algebra as a complex bundle, which is this thing, of course, using the tangent bundle or the cotangent bundle. It doesn't matter. There's a metric. And so in this case, we are spin C. So if M is an almost complex manifold, then you get a spin C structure. And this is sort of the canonical spin C structure in that case, and all the others are that tensor by a line bundle. The reason this is called a spin C structure is just that spin C is sort of the automorphisms of all this. So spin C is the automorphisms of W. It's pairs, an automorphism of W with an SO automorphism of V, such that the actions commute with the Clifford multiplication, the Clifford action. And the point is you've got an additional bunch of scalar automorphisms of this, which commute with the automorphisms induced by the Clifford action. So in other words, there's an exact sequence like this. And so if we start with a bundle with structure group SOV, we're trying to lift over the overlaps the transition functions in here to be elements of here. So we're trying to sort of split this sequence, and that may not be possible. So there's an obstruction in the cohomology of this. Okay? But this extension restricted to the unitary group sat inside here is actually trivial. So you can always lift that, and that's why you always have this spin C structure in the complex case. But the point is, on 4 manifolds, classical result in topology is that there's always a spin C structure. And once you've got one, then you have a whole set of them given by tensoring by line bundles. So that's why you get an affine space based on the first Schoen class of the line bundle. So what's the proof of that? Well, it's very complicated in German, but you can make it much simpler just by using almost complex structures, as I've tried to do over there. So the point is that 4 manifolds, the first obstruction to the existence of an almost complex structure actually vanishes. So an almost complex structure is actually equivalent to a self-dual 2 form. So this is the standard thing that metric plus complex structure give you Kähler form plus metric give you complex structure, etc. Okay, so once I've got a Riemannian metric, I pick a complex structure. That gives me a 2 form by the usual formula. It turns out to be self-dual. And similarly, if you have a 2 form, you get an almost complex structure. And the point is that the first obstruction to doing this vanishes. So the Euler class of this bundle of self-dual 2 forms, so you're trying to pick a section of this, vanishes because it's got odd rank. It's a rank 3 bundle. So we can actually pick a section. So this is a rank 3 bundle. Its Euler class should be represented by a 1 manifold where the section vanishes. That one manifold vanishes. So at least in codimension 3, we can pick an almost complex structure. You may still find that there are obstructions at points. But the one-dimensional obstruction vanishes. So in other words, we can get an almost complex structure away from a finite number of points. And that gives us a spin C structure away from a finite number of points. But spin C structures are more flexible than almost complex structures. One implies the other, but not the other way around. And so you can actually, even though you can't extend the almost complex structure across these points, you can extend the spin C structure. Okay, because you have a spin C structure away from these points. You can obviously pick any old spin C structure over a small ball over these points, which is contractible. And then they differ on the boundary by a line bundle, but line bundles on the 3-sphere are trivial because they're given by maps of the equator into U1, which is 0. Okay? So all 4 manifolds have spin C structures. And finally, another little bit more of Clifford nonsense. The Hodge star, there's sort of the top form in here, multiplied by some constant, acts as an involution. It has square minus 1, so it splits this your spin C structure, your Clifford module, into 2 pieces, plus or minus eigenspaces, plus or minus 1 eigenspaces, and it anti-commutes with the action of the vector space sat inside the Clifford bundle, the original vector space. So this action of this Clifford action restricted to the original vector space swaps W plus and minus because the original vector space anti-commutes with this guy here. And again, you should always think of the almost complex case. It's very instructive, tells you what's going on. What you find is that your spin C structure is just the complex exterior powers, the holomorphic cotangent bundle, and the W plus is the even parts and W minus the odd parts. And the Clifford action exchanges these two, obviously. Wedging takes you up a degree and contraction takes you down a degree. So it swaps even and odd. And then there's something called the line bundle associated to a spin C structure, which in our case in dimension 4 is just the wedge 2 of this W plus, and it transforms it's square. If I change the spin C structure by tensoring by a line bundle, the associated line bundle to the spin C structure transforms by squaring that. So those are just some facts that you need to know to set up the equations. And to set up the equations, we need to be allowed to differentiate, and the right way to differentiate in these Clifford bundles and spinor bundles is with the Dirac operator. So the Levi-Civita connection, I'm just working on the tangent bundle now. The Levi-Civita connection tells you how to parallel transport in the tangent bundle. The Clifford algebra and the endomorphism algebra of W, well, that is the endomorphism algebra of W, or the projective bundle of W, are all canonically determined by the tangent bundle. So as you parallel transport tangent vectors, you can correspondingly parallel transport in these bundles. So you get a connection induced on the projective bundle or the endomorphism bundle of W. So the only discrepancy is you need to pick a connection on this central bit, the line bundle that's sort of left over. And so it turns out that using the Levi-Civita connection to induce a connection on this spin C bundle, it's enough just to pick a connection on that associated line bundle over there. And then we have something called the Dirac operator, and it's given by this. Okay, so in all my notation, A and B are roughly the same thing. A is the connection on the line bundle. That induces, with the Levi-Civita connection, a connection on the spin C bundle. So A induces B and vice versa, because B is compatible with the Levi-Civita connection. And so we get this Dirac operator given by, well, we differentiate sections of the spin C bundle using the connection. That takes us to here. Using the metric, we go to the tangent bundle here. Now we can use the Clifford action and multiply. So if this Clifford action was just wedging, this would mean we would differentiate and then wedge with the thing we differentiated with. So that would be the exterior derivative. But there's an interior product as well. Okay, so it's slightly different. Okay. Anyway, so that's the definition. Turns out to be self-adjoint operator. It also switches W plus and minus. But it's just a differential operator, something a bit like a connection or an exterior derivative associated to a connection in a line bundle. And so again, what happens in the Kähler case? Now, we need to be Kähler here, not complex or symplectic. We really need that the Levi-Civita connection is actually the Chern connection on the holomorphic tangent bundle. We need that it's compatible with the complex structure. So that's the Kähler condition. The Kähler condition says the Levi-Civita connection equals the Chern connection on the tangent bundle. Okay, so in this case, the Dirac operator is what I said it was, d bar, but plus the interior product gives you d bar star. Okay, so the claim is the Dirac operator is d bar plus d bar star in this bundle here. So let's take the mu is 0 case. So there's no line bundle. Then the Clifford action was, if you remember, say the Clifford action on this exterior, this complex exterior power, it was wedging an interior product. But that was the Clifford action of the holomorphic tangent bundle, or the 0-1 forms under the metric. That was the Clifford action of the 0-1 forms. But the 0-1 forms can be identified with the original tangent bundle or cotangent bundle, the real tangent bundle or cotangent bundle. But when you do that, of course, you introduce 1-0 forms. You introduce forms of mixed degree. So when you take something in the cotangent bundle or tangent bundle and you wedge, you end up with things of mixed degree, and you have to project back into the 0p forms. And when you do that, you introduce this factor of √2. Okay, so the Dirac operator up to a factor of √2 is given by you differentiate, and then that gives you a cotangent bundle piece, and then you use it to wedge and inner product. Okay, well, the wedging part, let's do that first. So you differentiate and wedge. Well, that's just the exterior derivative. And then you project to this part, this 0 part again. So that's just the d bar operator. And then similarly with the interior product, that's the adjoint of wedging. So lo and behold, you get the adjoint of d bar. So you can just you can express the interior product in terms of wedging by using the Hodge star and its complex conjugate. When you chase that through, what you end up with is star bar, d bar, star bar, which is the which is the adjoint of d bar. Okay, so this is an elliptic operator. That's what it looks like. And the final thing we need to set up the Seiberg-Witten equations, as I say, now once we've done it for completeness, you can forget all about it, is that the curvature as a two-form, well, the two forms sit inside the Clifford algebra, because the Clifford algebra was all forms, all exterior powers. So it gives you an endomorphism of the spin C bundle. And when you chase through these identifications in 4 dimensions, you find that the self-dual two forms, tensor with C, give you the trace-free endomorphisms of the plus part, the positive spinor bundle. Okay, so that's just a fact. So the curvature, the self-dual part of the curvature, this gives you an endomorphism of W plus. Okay, under this Clifford multiplication. And actually, that's an isomorphism. Okay, so now we can set up the Seiberg-Witten equations. So far, we've always talked about gauge equations, which are just an equation for a connection. There's many other examples, like Hitchins equations, Higgs equations, so on and so forth, which are equations for a connection plus some auxiliary field. So some section of the bundle which your connection is on, and there'll be some equation for that section. It'll be holomorphic or parallel, or its derivative will square to give you the curvature, or whatever. Okay, and then these are of those form. These are of that form. So you have a section of this positive spin C bundle, and a connection on the line bundle which induces, I've got a metric on my manifold, Levi-Civita connection. This induces a connection on here. And the equations are, there's an equation for the curvature and an equation for the section. So the section, it says that its Dirac operator is 0, and the equation for the curvature is that the self-dual part of the curvature as an endomorphism of W plus is this thing. Okay, so this is clearly an endomorphism of W plus. It's what that means, of course, is the following. The endomorphism given by inner product with phi. So it takes something, inner products it with phi and gives you phi back. That's an endomorphism. Take its trace-free part. Okay. These equations then have a gauge group action just given by the gauge group action on the line bundle, acting on connections on the line bundle. Okay, so it's actually a linear gauge group action, a abelian gauge group action. So it turns out the equations are very simple. These are, roughly speaking, just equations on a line bundle. But they are nonlinear because of that phi star term. And that phi star term is cool. If you got its sign wrong, you'd be in trouble, because it gives you all the estimates to give you compactness. Okay, so if you're unhappy with spin C structures, you just need to know there's a PDE. And we'll do a very little bit of analysis, much quicker than last time. Again, if you don't like analysis, you don't need to know this. But the nonlinearities there give you estimates very quickly, which give you compactness of the moduli space. So I'll just give you one of those estimates. The Lichnerovich, whatever you say, formula says that the second order sort of Laplace type operator you get from the Dirac operator in its adjoint differs from the full connection in its adjoint by this term here due to the connection. So if the connection was flat, that wouldn't happen. Plus this term here due to the Levi-Civita connection. This is the scalar curvature. So if you then inner product with your, so dA phi is 0. So you know, inner product with phi, you get this inequality here coming from that, because I've plugged in the FA plus is phi star trace-free part. So you get this inequality. I've replaced S by its minimum. This is a general fact, how you relate. This is a pointwise inequality. If this was L2, then I could just take the adjoint over to this side. Pointwise, I can take the adjoint over to this side plus some divergence term which integrates to 0. And that's the term Okay, so that's just the property of it being a formal adjoint. This is something exact, so it integrates to 0. So you plug that in there, and you find this. Okay. So any maximum of the spinner here, the Laplacian is positive, or 0, because we're at a maximum. So you find that the maximum of this norm squared of this spinner is less than minus a half the minimum of the scalar curvature. So for instance, if the scalar curvature is positive, then the spinner has to be 0, and all the solutions are trivial. Anyway, so we get this sort of L infinity, this pointwise bound on the spinner, feeding that back into this equation. We get a pointwise bound on the self-dual part of the curvature, and from that, compactness follows quite easily. Just sort of standard methods following on from Donaldson theory. Okay, a little bit more analysis. We want to do transversality now. But for this, it turns out you really need to perturb the equations. That doesn't mess up compactness by adding a self-dual 2 form onto the curvature. So this is so simple that Witten did it. So you wouldn't expect him to do the analysis. And this makes the equations transverse, and you get a compact moduli space of this dimension, given by the first Chern class of that spin C line bundle. This is the Euler characteristic of the manifold. This is its signature. Remember, all our 4 manifolds are simply connected, or have B1 equals 0 at least. There's a gauge group action, which acts by scalars on the spin C vector bundle, and so by weight 2 on its determinant. The fixed points, as you can see from this, only occur when the spinner vanishes. But if the spinner vanishes, then you end up with, from the equations, if the spinner vanishes, then FA plus vanishes. And so we're back to, and remember, this A is a connection on a line bundle. So we're back to these reducibles that you saw in Donaldson theory. You're back to the curvature of the line bundle being anti-self-dual, so its first Chern class is in H2 intersect the harmonic self-dual 2 forms. So again, you've got a lattice and the anti-self-dual 2 forms. So if the if B plus is bigger than 0, so that this has codimension, then you can hope to avoid these. If B plus is bigger than 1, you can hope to avoid these in a 1-parameter family. We've seen that before. Okay, so once B plus is bigger than 1, we get a compact, smooth moduli space. For a generic metric, we avoid the reducible bad solution where the gauge group action is bad. The gauge group action we deal with as before by Uhlenbeck's theorem. It's all very easy. And then what Seiberg and Witten tell us to do is to restrict attention to moduli spaces of dimension 0. So this is one of the magical things about Seiberg-Witten theory. We don't have to do any intersection theory. At least conjecturally. Or at least for simple type manifolds, but I don't want to tell you what that is. So restrict attention to spin C structures satisfying this condition. That's the same as saying that the dimension of the moduli space is 0. And then you just count the points in the moduli space, and that's the Seiberg-Witten invariant. Okay, so this is really a fair bit simpler than Donaldson theory, although a little nastier to write down. And the conjecture of Seiberg and Witten, partly proved in some cases by Finn and Lennes, building on work of Pistorius-Turin, is that the Donaldson polynomials are determined by they give an explicit formula in terms of basic classes, which is what this refers to, and I haven't told you what basic classes are, but they're determined by the Seiberg-Witten invariants. So just by these counting of solutions. So you just count some solutions of a PDE, and these are really deep invariants of a 4 manifold. Okay, so again, I want to just briefly do the complex case. So I should say, using these invariants very quickly, people proved most of all the old results of Donaldson's and all the results of other people using the Donaldson polynomials much more simply using these invariants. Some of the arguments appear a little less geometric and a little less nice. For instance, Donaldson's first theorem, where you got that nice cobordism from the manifold cones on P2, that result again is proved very easily using Seiberg-Witten theory, but a little less geometrically. Okay, the complex case. So remember, for Donaldson theory, we just had this relation that the Donaldson polynomials didn't vanish in the complex case. So on a Kähler surface, we have our positive spin bundle. This is just the 0 forms plus the 0,2 forms twisted by a line bundle. And so our section splits into two pieces. There's a function or a section of a line bundle and a 0,2 form. And the equations, well, we already saw the Dirac operator. And then the equations for the self-dual part of the curvature. Remember, the self-dual 2 forms on a 4 manifold look like the 0,2 forms plus the complex conjugates and the omega part of the 1,1 forms. So you get an equation for both of those, and that's what the equation is. And then these are very easy to solve. There's two different cases. One is where the degree of the line bundle coming from this, so that's mu squared times the canonical bundle. If that's negative, then beta always vanishes. If it's positive, then alpha always vanishes. If it's 0, then they both vanish. And so the equations become very simple. They just reduce to this case. In each case, remember, look, we immediately get a holomorphic interpretation, just as before, because the 0,2 part of the curvature vanishes, because this product vanishes. And so you get a holomorphic structure on your line bundle. So, as before, we're managing to get a holomorphic interpretation. Excuse me. So, the proof, very briefly, you just apply d bar to this equation. And you very quickly get d bar squared here, which is this 0,2 part of the curvature, which by one of the other equations is given by this. There's a half missing. I'm not sure what happened there. And so we get this formula here, inner product with beta, integrated with the manifold, and we find that we get d bar star of beta modulus all squared plus this equals 0. So we get the sum of two positive terms, so they must both vanish. So we find this. Okay. So one of alpha or beta is going to have to vanish on an open set, and then by ellipticity and analytic continuation, it actually vanishes everywhere, because these are nice elliptic smooth equations. So one of them vanishes, at least. And this equation has become two equations. Both of these terms vanish, because this one vanished. Okay, and then the degree decrees which one must vanish, because the degree of the line bundle is given by this formula, and therefore the sign of it is determined. If alpha vanishes, this is going to be positive. If beta vanishes, it's going to be negative. So the degree of the line bundle decrees which of alpha and beta vanishes. Okay, so that's what we end up with. So, we don't have to solve the Hermitian-Yang-Mills equations or do Donaldson-Uhlenbeck-Yau. This is an example of why it's much simpler. What's amazing is that these moduli spaces contain so much deep information. So in the Kähler case, if we're on a Kähler surface, this condition that the dimension is 0, so we're looking at zero-dimensional moduli spaces, that's actually the condition that, it turns out, that the line bundle is the spin C structure is the canonical one. So our mu vanishes. We didn't twist by any line bundle. So or it's dual. There's always a Serre dual to all these. You can always replace the tangent bundle by the cotangent bundle. Okay, so the line bundle is the canonical one. And do I want to say anything about this? Yeah, the line bundle being the anti-canonical one can be related back to the line bundle being the canonical one by just the Hodge star. These alpha and beta are just related by a Hodge star. So for every alpha argument, there's a dual beta argument. So I'm just doing one of these arguments. So we also want to remember B in the case where B plus is bigger than 1. Well, remember on a Kähler surface, where the self-dual 2 forms are isomorphic to the 0, 2 forms plus their complex conjugates plus the span of omega. This is all compatible with the Hodge star and the metric and the Laplacian. So the same thing happens at the level of harmonic forms. This decomposition commutes with the Laplacian. So we find that the harmonic forms are given by H02, this Hodge space, H2 of so this holomorphic Hodge number here, plus the span of omega in cohomology. So in particular, its dimension, B plus, is given by B02, which is also equal to B20, which is equal to the dimension of the Serre-dual of this, H20, which is the dimension of H0 of wedge 2 of the cotangent bundle, so canonical bundle, plus 1. Except I've missed a 2 out, haven't I? Because there's some complex dimensions and some real dimensions. Okay, well, it's not in the notes, so it doesn't matter. Anyway, the point is, for B plus bigger than 1, I'm going to need some of this. So the canonical bundle is going to have to be positive, not negative. So we're in the degree of the line bundle being positive case. So we know that it's beta that vanishes, not alpha. Alpha is now just a holomorphic function, in fact, because the line bundle was trivial. So it's actually just a constant. That constant's determined by this equation. And so we find that we get a unique solution. Okay? So there's a unique solution to the Seiberg-Witten equations on a Kähler surface. And you can show it's isolated, and therefore it counts as 1 or minus 1, depending on the orientation. And in fact, Taubes has shown this extends to symplectic geometry. So because the analysis is easier, you can actually extend this theorem to symplectic manifolds. That, of course, is incredibly hard. But nonetheless, it's easier than doing it in Donaldson theory, which no one's ever managed to do. And just very briefly, as an aside on some of the other results in this area, Taubes has also managed to relate Seiberg-Witten invariance to Gromov-Witten invariance via the 0 set of this section of this line bundle. So this alpha is it's holomorphic, or if you're on a symplectic manifold with an almost complex structure, you can so asymptotically, under some perturbation going to infinity, it becomes pseudo-holomorphic. And this gives you a curve. Its 0 set gives you a curve in the manifold, and that relates Gromov-Witten theory to Seiberg-Witten theory. And other applications include the Thom conjecture. So if you have complex curves in Kähler manifolds or even symplectic manifolds, you can deform the manifold and the metric around this curve. You can extend its neck, as the kind of thing I was doing yesterday, and solve the equations under those conditions and find the following kind of results. This is the prototype of that result, is the Thom conjecture, that smooth complex curves in CP2 have minimal genus of any representative of their homology class. So you can obviously always increase the genus of a representative of homology class by adding null homotopic handles. It seems a natural conjecture that complex curves would have minimal genus, and that indeed is true. So there's extensions of that even to symplectic manifolds, using pseudo-holomorphic curves and symplectic curves. Okay, so I was rushing a bit because I wanted to explain Bauer-Ferruter invariants. So these are a generalization of Seiberg-Witten invariants. Less people know about them, and it's very pretty. So I wanted to explain these invariants. So first I want to go back to finite dimensions. Eventually this will be applied to some infinite dimensional situation, some space of connections and some infinite dimensional bundle over it. But let's go back and do some finite dimensional topology. So suppose you have a proper function from Rn to Rn. So proper means it goes off to infinity. As you move to infinity, the image moves off to infinity. so much so that the inverse image of a compact set is compact. Okay, then you find all of its fibers are compact. They're generically zero-dimensional, and you can count the number of points in a fiber. So this is some cover. You can count the degree of the cover, the number of points in a fiber. And that's the kind of thing we're doing in gauge theory and Seiberg-Witten theory. We're counting the number of points in a moduli space. So we're counting the zeros of some map, where the map is this Seiberg-Witten map, and this Rn is R infinity in that case. But you can express this number of zeros of a map in a different, more topological way. Because F is proper, we can extend the map to the one-point compactification of Rn, which is the sphere. And now you can just take the degree of this map. So think of it as a homotopy class of maps from the sphere to itself. And you can take its degree, which is this homotopy group. And that number, so the number of times it wraps the sphere, is the number of points in the generic fiber. Okay, now, so that's the zero-dimensional moduli space case. That's where you have the zero-dimensional space of solutions. Zero set of this function is zero-dimensional. If you're in the case where the zero set is positive dimensional, so we're mapping from some bigger space to a smaller space, again, if this map is proper, then the fibers are compact. And what we've been doing is considering the moduli space up to cobordism. So by taking a generic fiber, we get a smooth, compact manifold. That's our solution set. If we take a different fiber, by connecting it by a path, we get a cobordism to this other fiber. So we get up to cobordism, we get a solution space, some n minus n manifold. Instead, though, again, we can compactify and get a homotopy class of maps from the sphere here to the sphere here. So there's two different things we can do. We get a cobordism class or an element of a homotopy group. But you get more than a cobordism class because the fibers of this map all have trivialized normal bundle. Because they're the inverse image of a point, and a point has a trivial normal bundle, clearly. It's just the tangent bundle of the point downstairs. So when you lift that up, you get a trivialized normal bundle upstairs. So in fact, we don't just get a fiber up to cobordism, we get a fiber with a trivialized normal bundle up to cobordism. So we call this trivialization a framing, so we get a framed fiber, the framed normal bundle, up to framed cobordism. So we take the inverse image of this point, or the inverse image of this point. We can choose a path going between them. The normal bundle to this point is trivial, the normal bundle to this point is trivial, and the normal bundle to this curve is also trivial, and all the trivializations stick together properly. So we actually get a framed cobordism upstairs. So to any element of this homotopy group, by taking the generic fiber, we can associate a framed cobordism class. And the Ponte-Argon-Thom construction notes that we can actually do the converse. So conversely, given anything which will eventually be a fiber, any n minus n manifold in the sphere with framed normal bundle, well, what does that give us? That gives us an isomorphism between the trivial bundle and the normal bundle. Well, the normal bundle, by the tubular neighborhood theorem, looks like a neighborhood of this manifold in the sphere. So this framing gives us an isomorphism between the tubular neighborhood. So I'm inside the sphere. This is my manifold. This is a tubular neighborhood. This is a tubular neighborhood. And by the framing of the normal bundle, this is that gives us an isomorphism to M times R n. Okay. So that's what a framed normal bundle gives us. It gives us an isomorphism from a neighborhood of this manifold to here. But this obviously has a map to Rn. The projection map, so it just tells us how far we've moved away from the manifold. And then we can complete this. So this is sat inside the sphere. This is sat inside Sn. Then we can complete it in the obvious way. We map the boundary here is mapping to infinity in Rn, so we map everything else to infinity in the sphere. So you map all of this to infinity. That gives you a continuous map. So you end up with a map from Sn to little sn. So you end up with an element of this homotopy group. Okay, so there's a one-to-one correspondence between these frame cobordism things, manifolds, and these homotopy groups. And then we can stabilize this. We could do this in higher and higher dimensions by timesing by r. Similarly, we can stabilize this. If you have any map of a sphere to another sphere, you can suspend both of them and get maps between spheres of one higher dimension. And so you end up with this isomorphism between the stably framed cobordism group. That means manifolds with stably trivial normal bundle. After adding trivial bundles, you get something. You may start off with a non-trivial normal bundle. After adding copies of Rn, you end up with something trivial, so you can then do this construction in higher dimensions. Okay, so there's this isomorphism between this stable homotopy group, which is some limit of passing to higher dimensions, and the stably framed cobordism group. In particular, in 0 dimensions, so where your spheres are of the same dimension, this group is indeed isomorphic to Z, and it's still counting the number of points in your fiber. It's just counting the degree of the map. So you haven't lost that information, at least. So the Seiberg-Witten invariant in particular is going to be contained in that. The one that we already know is contained in that 0-dimensional group, so we haven't lost any information. Okay, so Bauer and Fruiter do an infinite-dimensional version of this, where the difference in dimensions is a Fredholm index. So you have a map between Banach manifolds, and it's a Fredholm map, so we can talk about the difference in dimensions. So in other words, its linearization has finite dimensional co-kernel and kernel. And so what they managed to do is, instead of getting a cobordism class of moduli space, which is what we did in Donaldson theory and in Seiberg-Witten theory, they managed to get a stably framed cobordism class of moduli space. In other words, they managed to get an element of this stable homotopy group here, where this n minus n here is the index of the problem. This is the virtual dimension of the moduli space. So they end up with an element of this. In the case where this is 0, that just gives you Z as before. That's not so that's what you would like to do. There's a slight complication due to the gauge group, so let me explain that. So the problem is, the Seiberg-Witten equations really aren't just the 0 set of a map. We have to divide out by the gauge group. In the Donaldson theory, this is very, very difficult. We can't just replace dividing out by the group by a slice, i.e. by a map, 0 set of a map. We can only do that locally. But in Seiberg-Witten theory, the big difference, the reason we can do all this, is because everything's abelian, we can work globally in U1 gauge, in Coulomb gauge. So we can, just through Hodge theory, everything's linear, and we can work, instead of dividing out by the gauge group, we can just impose that d star of the difference of two connections is 0. Okay? So instead of dividing by d of a function, we just work in the kernel of d star. And the only thing we miss there is the center of the constant gauge transformations, which obviously fix their stabilizers of any solution. So we've still got a U1 we have to divide out by at the end. So that's a minor complication. But so we consider the Seiberg-Witten equations as genuinely a nonlinear Fredholm map from some infinite dimensional vector space to another infinite dimensional vector space. We can then, because everything's Fredholm, we can go through all this procedure by finite dimensional approximation. We can get back to this situation over here, and all we've got to do is divide out by a U1 at the end. So the way they do that, just very briefly, is this map, this Seiberg-Witten map here, is of the following form. It's a Fredholm linear operator, which we understand, plus something compact, a compact operator, something very small. That's the nonlinear part here. The reason it's compact is because we work with some Sobolev space over here with one more derivative than this Sobolev space over here. So this is of 0th order, so it's compact by the relic lemma. If you don't know any Sobolev spaces, you can ignore all this. Roughly speaking, it's just a perturbation of a Fredholm operator. So you can take finite dimensional approximations of this infinite dimensional Banach space here, completed to be a Sobolev space, and you can look at their pre-images on the other side and work on those. So this is finite dimensional, this is finite dimensional. And remember, you've got this S1 knocking about. You have to do everything equivariantly with respect to this S1, so you can divide by it at the end. The equations are proper. That's this extension of compactness. It's better than the moduli space being compact. The equations are actually proper. And so what you end up with, well, you end up with, as I say, a map between these spheres. D is the virtual dimension of the problem. But we've got this plus 1 because we haven't divided by the U1 yet. So we end up with a map in here, which we'd like to divide by U1. Now, there's a slight problem with keeping track of this S1 action because everything works equivariantly except the transversality. So S1 equivariant transversality is very difficult. And so they get into lots of technical problems producing a more refined invariant than that one I've just given you over there. So there's a better invariant than this, but I'm not going to tell you about that because I don't understand it. But in the case where B plus is bigger than 1 and you have a zero-dimensional Seiberg-Witten moduli space, we end up with this one-dimensional cobordism class. So a map from an Sn plus 1 to an Sn, which is S1 invariant. You can take its fibers, divide by S1, and you get a number of orbits. So you just count orbits, and that gives the usual Seiberg-Witten invariant. Okay. So you're always getting something of one dimension bigger because you've got this circle action. Okay, so that's the Bauer-Ferruter invariant. So it lies in here, and they managed to get some equivariant version. Okay, and the application is the following. So this is pretty. So if you remember the Donaldson invariants, and also, in fact, for the same dimension reasons, the Seiberg-Witten invariants of connected sums just vanish. So the proof's the same. In the Seiberg-Witten case, you want to take zero-dimensional moduli spaces. But in that case, you want them to be zero-dimensional on both sides of your connect sum. And therefore, the total dimension of the thing is one-dimensional because you've got this U1 gluing parameter. So it doesn't work. So, but the Bauer-Ferruter invariants do something good under connect sums so that you can get better invariants. Oops. So Bauer shows that their invariant in that stable homotopy group is the product of the two invariants, of the two manifolds. So what this product is sort of obvious. If you think of it as just cobordism classes of moduli spaces, it's just the product of moduli spaces. So that's this gluing thing I was telling you about before, roughly speaking. If you think of it in terms of maps of spheres, it's just the composition of two maps of spheres. So if you have a map of some Sn to some Sm, you can stabilize that up until it agrees with some other map of Sm to Sp, and then you take the composition of the two maps. The fiber of that is clearly the product of the two fibers. Okay, so you can think of this in many different ways. So you just take the product of these invariants. So that's this gluing. That's the generalization of this gluing formula. And again, gluing works better for Seiberg-Witten as well. And Bauer has some genius argument for proving this result here. Okay, so the gluing argument is roughly that the moduli space is the moduli space on both sides times by the U1 gluing factor to glue solutions across a neck. So we get this result. And so one application is that whereas before all the invariants we knew of K3 connect sum K3 vanished, we can now get a non-zero invariant. So the invariant of K3 turns out to be the stable homotopy class of the Hopf map, S3 to S2. Okay, so that has fibers a single circle. When you divide out by that circle, you get a 1, and that's the usual Seiberg-Witten invariant of 1. But it's a classical topological computation that the square of the Hopf map, which is in some second stable homotopy group, is non-zero. So the invariant of K3 connect sum K3 is non-zero. But the invariant of S2 times S2 is 0, so actually K3 connect sum K3 can't split off any S2 times S2s. That was a question that came up in the second lecture, or the third lecture, if you remember. So we knew from Donaldson theory that K3 couldn't split off an S2 times S2, even though its intersection form looked like it could. And Bauer can show that K3 connect sum K3 also can't split off an S2 times S2. And in fact, again, this is all can be generalized to symplectic, due to Towns's results, can be generalized to symplectic manifolds. under this condition that B plus is 3 mod 4. Okay, thank you very much.